introduce the moderator. Today's moderator is George Kenney, among friends Buzz Kenney, co-founder and president of EntraTympanic, also himself a serial entrepreneur, but with a long background from MIT, which he may or may not have time to explain here.
Before we get going, I'd like to take a minute to say a couple of things. The title for this panel is The Future of Nanotechnology and Advanced Materials. And we have the experts to discuss essentially nanotechnology and advanced materials. I want to just focus on the issue of future for a moment. I would like to remind and provide essentially some context and a foundation for essentially the discussion. When you think about the future, the only way you can figure out where the future is and where you're going is if you understand the past. And I would remind you that a few years ago, the space we're sitting in right now was an open parking lot. At the end of the 60s and the early 70s. It was an open parking lot before essentially a technology miracle happened. And that began in the early 80s when when Biogen and the Whitehead Institute came to campus in 1982. The Whitehead Institute at $135 million created one heck of a discussion on campus as to whether it was appropriate or not, right? I remember the discussion. It was heated. Whitehead started up, Biogen moved in, and the rest is history, which brings us essentially to the current day. Where do things go from now? I mean, we have the past, we have the present. What's the future? Well, the future is, in my opinion, being defined by a building being built not on the edge of campus, but right in the middle of campus. Thank you very much, Vladimir. A lot of people are upset with the distraction of walking all the way around it, but they'll get over it, not to worry. They'll get over it. MIT has made a decision, a $450 million decision, to build a new nanotechnology center right in the middle of campus. I don't think MIT's ever done that before.
It's the biggest structure we ever built, and most expensive building, and the most disturbing building from perspective of disturbing the campus. But it's going to be footsteps away from 75% of everyone who wants to use it. So when it opens 2018, it will be as easy to reach as it right now. The noise is easy to hear. So.
You know, Vladimir's office is right next to that. So
yes, I am.
No one can complain because
he can keep an eye on it. But the interesting thing about that structure, I noted in your presentation, you talked about 50% of the faculty in the School of Science and 60% of the faculty in the School of Engineering being essentially involved in nanotechnology in one way, shape, or form. It is consistent with the MIT model that that structure be where it is. I looked at it and I smiled the first time I saw it because it literally is at the node. It brings everything together: biology, bioengineering, physics, chemistry, advanced materials, electrical engineering, and everything else.
Yes, and also it has no faculty offices. Why waste the space on things like that? And similarly, no student offices because they're footsteps away from the building itself. So it's 215,000 square feet, and it's all shared lab space.
Right, with no faculty space. So this is all for graduate students. Another basic left turn, which way am I pointing here? Orthogonal shift in essentially the culture of academia in terms of no faculty in that space. All students, all graduate students, and hopefully a few companies.
Yeah, so the way to think of it is that MIT does one thing really well, and next year is going to be 100 years from the construction of the present campus. MIT used to be in Boston, right, in Copley Square, and it was too noisy and too dusty, so we moved into the suburbs. Now we need lack of noise and lack of dust, which is this MIT.nano building we're building again, and it's just extending the culture of MIT, which is that when we built the campus 99 years ago, we want to make it easy for chemists to walk from one lab to another. So there are no doors, right, as you go down the infinite corridor. It's very easy to step from one discipline to the other, and actually that defined MIT, right? I mean, we have no boundaries between departments. Cross-discipline interaction becomes very, very easy. So MIT.nano's goal is just extend that. Just make it so that we have an even bigger space and a tool set that none of us can afford as individuals, but as a community of half of MIT users, we can, right? And I don't need all those expensive equipments 24 hours a day. I'll share, and everyone else will, in order to get us all to be able to up significant amount from what we can do today.
Mm-hmm. So basically, it's a shift in paradigm. It's a shift in architecture. It's a shift in principle.
Yeah.
So basically, what will the neighborhood look like in 10 years, 20 years, 30 years? Are some of those companies basically going to be occupying those buildings that have names like Novartis and Pfizer and Biogen on them?
Yeah. Well, so again, I don't mean to monopolize the discussion here, but if I look at most of the hardware startups that are in the material space, typically round day of their funding that they raise, most of it will be spent on reproducing the capabilities they used to have while they were students at MIT, right? Isn't it a hood space or vacuum growth systems? That's a lot of both equity of the company itself and also a lot of time, probably a year and a half of bringing up a facility that already could have just been used at MIT as an external facility. Mm-hmm. The challenge today is that the time we have that's available on our present tools is so tight that 10% of MIT users actually go to Harvard. Well, pardon me, I'll put it another way. 10% of the income of Harvard facility comes from MIT accounts. Because we just don't have enough time on our own tool sets to go ahead and do the work we want to do. Mm-hmm. We're going to double clean room capabilities, centrally shared, imaging capabilities, centrally shared. We're going to develop a new prototyping facility we never had, all within this one central building, MIT.nano, which should transform what we can do and also what it means for us to enable others off the street, our alums typically, who have seen MIT and know what MIT can do, to come in as affiliates of MIT.nano to utilize the space, both bringing us the value to our students to know what is it that the world needs, and also at the same time providing them the accelerator, the place that they do not need to build right off the bat, first year and a half of their time and the first $5 million of their round day funding towards reproducing what they used to have. You can use what you have right now. And at the end, validate round A by having a much stronger position with much stronger prototypes that should give you a higher valuation in round B and so on and so forth. So we should be able to accelerate the process dramatically by utilizing, essentially extending into the alumni eras what we do as students at MIT.
Okay, so there goes my introduction.
Ah.
There's the future, right? Thank you. Perfect. Basically, we have we know what the past looks like. We know what the future, the present looks like. Now we have essentially this opportunity to step forward into the future. All of the panelists have basically had some airtime this morning, I think. Yes. So no need for introductions, I suspect, if we're okay with that. But and Adam, I understand you have to sneak off to talk to an investor, I guess.
An ILP connection.
Excellent. Okay, so we'll take care of that in a few minutes. So basically, the questions that we're here to ask and answer, hopefully in the next 30, 35 minutes, basically, what are the challenges? What are the challenges of getting from here to there, given essentially that we think in terms of months, years, and a couple of decades? Does anyone want to start with that? What's the challenge? How do we take the technologies and the nanotechnology we have right now? How do we progress through this system to get to where potentially biotech and bioengineering is in Kendall Square right now? In 5 minutes. You want to take the first question?
Yeah, sure. So I think Vladimir addressed this. I think commercializing a technology is a very simple formula of you need to sell it for more than it costs to make. So that's two components. Is finding a very strong need for the technology. You can't just push it where you think it's going to go. You have to firmly establish that there's a market for it. And it's all about manufacturability in the end. I think working with Kripa over in the LMP, the Lab for Manufacturing and Productivity, is where CNC machines were born. We're definitely very close to the manufacturability end of things. We always wear that hat because it's important to design in the manufacturability as early as possible. So again, talking to the companies and corporations, the ILP partners, to inform as early as possible to design in manufacturability into the technology is crucial.
What does the timeline for manufacturability look like in the context that you're talking about with, for example, with thermal power generation and essentially improving the condensation efficiency of the reactors? What kind of timelines do you have to deal with?
Yeah, as I said, being able to leverage the infrastructure, the physical infrastructure, for example, using a chemical manufacturer's on-site little baby power plant as a test point to get into the larger 100 megawatt units. You need to prove out half a year to an entire year of even accelerated durability trials, and that's often very difficult for a young startup to be able to afford. So this is why the cooperation with these established partners is key.
Excellent. Okay. John, did you want to add to that?
Yeah, I guess the one thing I was thinking about and following up on Vladimir is that one of the other reasons that I think having more capability at MIT in the early days for a company is very often the technology and the application that's targeted when you start a company isn't exactly where you end up, right? And investing time and money in building, replicating capabilities that at the end of the day aren't really what you need to have. And certainly that's the experience I think at QD Vision that we had, is that it took years for us to really explore and find the right application and focus for how we're going to bring our technology to the market. And learning from that to accelerate that process, I think is one of the challenges going forward.
Mm-hmm. So that's a capital cost. That's a time and money issue in terms of facilitization, basically to figure out what it is and where you go from there. So partners become even more interesting.
So partners and getting through that initial exploration as quickly as possible to get focused.
Interesting. Venkat, would you like to comment on that from the corporate side?
Definitely. In the corporate, the R&D projects, once the scope, we understand the customers, OEMs or end users with whom we work very closely. They define the problem statement. Once it comes into R&D, it takes roughly, with a solution package and identifying a positive solution, maybe 1 to 2 years. In semiconductor, life cycle is 2 years is too long. So you need to work out quickly. And once the product is there, then it goes to the pre-production trials, and then 3 to 5 years it can take. So the whole project from the start to the end of the thing. So most of the times what happens is the manufacturable scalability, again, that is the issue which we constantly see. Internal, our own development also, we find a lot of challenges. We integrated recently a new company, a silicon-based company in Voltex, which is from New Jersey, that has given us the pilot and HVM manufacturability. Earlier it is much more challenging. Now we have that know-how, our internal know-how, what are the things we need to take into account, which we can integrate upfront in the lab. That's what I was articulating. Then we can make it much more process seamlessly. There are going to be much more challenges, especially, for example, I highlighted a thermal stability, which is a key component for the nanomaterials. If you're manufacturing in one part of the world and you are shipping the materials across the oceans, and what is the temperatures in the containers? It is elevating. And once elevated temperatures, is the nanomaterial true in the form, or its transformation or reorganizing? So those challenges has to be addressed. In order to do that, we do the acceleration test. That means we elevate the temperature of the material in a certain canisters and test and see whether we can see any degradation or survivability. So all we do parallelly, that will limit the time, but still doing all those things in parallel takes a couple of years once you identify the solution.
Once you've identified the solution, how do you identify the solution? How do you know it's the solution?
So in our company, we work with the end users, our OEMs, very closely. So the moment the project is launched, we have very close interactions, monthly basis. They know exactly where we are going, and anything turns and twists we need to do it, we can do it real time. So that gives us much more leverage and not to divert. Sometimes we talk about we need to know upfront all the information so that way we can turn back, or you can take a detour and you can make a different solution proposal. So this enabled us, and that is what makes successful for us.
Kripa, I want to come back to you. I want to not come back to you, but come to you. Basically, in your video, you showed essentially a bottle basically being coated. Was that done at MIT or outside of MIT?
So we did a lot of the initial manufacturing development at MIT, and so it was easy to then, put it into. So what we did at MIT was with a paintbrush.
Right.
So then we could put it into a more quality control process using a spray machine that was built by someone else.
Okay.
So I guess the key point is thinking about research for deployment is key, and not do not do various things because we have only a limited amount of time. So if you want to deploy this, have to have the basic science, but what is it that will make this product become real? Right?
So
And that's so for us at that point, sprays were so ubiquitous. So we didn't want to go and
develop a new manufacturing process. We wanted to use what's existing, what's already available, but change the input raw material that goes into the process. And I think with that, you can probably conquer most of the space. I know that for some things you may have to come up with a new process itself, but if we can think through and say, what processes that are there and how can we use them to deploy the science, I think that is the fastest way to get to market.
Yeah, it strikes me, you think of MIT, it's School of Science, School of Engineering, technology in the name. What struck me was you were doing more than the science and the engineering. You were actually going to basically piloting the process. That begs essentially a question as to what one of the challenges is in terms of taking nanotechnology and moving it forward. If we back up and look into our neighborhood and our biotech, life science neighborhood, there's a facility up the street called Lab Central, where literally you have an incubator that accommodates all of this literally wet lab development. It's sort of a step function between MIT, Lab Central, and then all of the giants in the neighborhood. Is there something like that going to be needed in the environment or in the ecosystem for nanotechnology?
I think that's what we are hoping the MIT.nano would be, that it'll become that powerhouse for really transforming and become that real test bed to take all these technologies to market. If you think about it, right, most of the times you need, for all the things we do, it's like you need some sort of a hood kind of a facility. You need some sort of a chamber, right, whether it be a furnace or some sort of a control chamber. So the kind of things we use, you can sort of classify them into a bunch of things that you can probably, like a bunch of facilities that you can have where we can sort of try out different things.
Okay.
So I think maybe thinking like that and sort of thinking about what are those common things that everyone uses and having that as a incubator center, those facilities, I think will make this, make it much more easier to take things forward quickly.
Okay, so it's an incubator center.
Well, it's in the, so I keep asking Vladimir, there's some space in that MIT.nano.
Again, the facility is shared but the way to think of it is indeed to reduce the risk.
Yeah.
If you look at typical venture capital investment into a startup company, they might see 100 plans, venture capitalists, in the course of a year, only to invest in one, and the reason in hardware domain. Right. And there's a very rational reason for that. I mean, at the end of the 5-10 year period, they'll spend $50 to $100 million on that one company, right? Right. Together, the consortium of VCs. So you really can't have too many of those hardware companies in your portfolio. Yet the guess they make, because they see 100 choices, make one option out of them, the one unicorn, right? That unicorn is not really vetted. I mean, all they see is a bunch of people excited. There is no facility. There is no really working team. So allowing them to make a much more informed investment, because MIT.nano enables you to put together a team, have it work without its own native facility, but utilizing the existing shared facilities, allows you to go ahead and gel the idea much more solidly. So when you do step in front of the VC and say, I'm ready, they'll have a team, a product, a strategy that is not fictitious on a piece of paper, but actually first steps have already been taken, right?
So you've already taken the first steps towards commercialization in this shared facility.
Yeah.
I think having a proof of product is much more powerful than just saying it's a proof of concept, right? I think with the Liquid Glide bottle, that's what happened for us. Like some random people in the airport were saying, oh, those MIT guys have solved this ketchup problem. I mean, people like complete strangers who are like trying to get, so that, has a huge, it gives you a lot of confidence, and all the investors have a lot of confidence.
Well, your video was also very interesting from my perspective. I had a big smile on my face because it's not often you see MIT scientists and engineers interviewing people on the street to talk about technology.
Well, no, that was CNN, actually.
That was CNN,
Yeah.
okay. That was CNN.
The other one, yeah.
How did you get CNN working for you?
No, they were excited about the video.
You should patent that, definitely. So basically, we're talking about it. Vladimir, you used the words shared facility. Let's talk about who's sharing. Certainly the faculty, School of Science, School of Engineering, grad students, postdocs. Anybody else?
Yeah, any of our external partners. So the idea is that, our knowledge and people, that's our product. This building is about education. And if that education can be by giving you access as a student to a whole set of tools you've never seen before and you won't see anywhere else, you'll be able to be much better prepared once you step out of MIT to define the next things the world needs to do. But at the same time, if I can attract into MIT.nano partners that say, we want to land that one of our researchers to be there in the environment for that period of a year, my students will get a much better education. We'll be able to go ahead and learn what is it truly matters. We'll be able to develop processes that could be then directly transferred onto other fancy tools in other fancy industries that choose to be working with us. So yes, no, I mean, having industry as a part of what we do is really important to us.
So Matt, how much square footage do you need in this facility?
Oh, as much as they'll give me. Actually, I wanted
So you won't get a single square foot.
Yeah.
You'll be able to use you'll be able to use 215,000 of it.
Yeah, it's actually really interesting, and the thing that I've been thinking about hearing the discussion a bit, and a little bit, it's a question I have for some of the people that are involved with starting up new businesses is. You often may have something that you think, hey, I can do something with this. It enables me to do something completely different or create a new benefit. And then someone else sees it and they think of a completely different application of it. And so I think of project teams that we have. We give them a problem. You must reduce the drilling time by X% or increase the reliability of this tool by 90%. And they don't know how to enable that. And so the ability to come in contact with people that might have that enabling component that will allow them to achieve their goal, that's a great opportunity. So if you can, and that's why we like coming to places like this and meeting people that have, that are working on interesting things and have some very specific knowledge and capability, because we might find that enabling technology that we can then invite them in and figure out how to turn that into a product or service that will generate revenues and solve practical problems.
Excellent. So basically this whole issue of science and technology transfers a body contact sport.
Absolutely.
You've got the arena. Let's get the bodies together and
we also provide majority of the bodies, right? I mean, it's about 2,000 bodies that you'll be able to bump into. I mean, it's the human friction I often say that leads towards innovation, right?
Which become your future employees. John, you've been awfully quiet here.
Sure.
What's your perspective on all of this?
Well, Xtalic started at MIT and spent
a
couple years incubating
Yeah.
here in the lab before we moved out. We moved out to Medford about 2 years in. So very close and still utilizing a lot of the equipment and the personnel at MIT to further the technology. At a certain critical point, we decided to move. We didn't have enough space. We didn't have enough access to labs here. And so we actually moved out to Metro West to build out a space there. But collaboration has continued to be a huge part of who we are. You invest in the tools that you need and are going to use readily every day to further your technology, but there are other tools that you need access to periodically. And so as we bring products to market, we actually collaborate quite heavily with the supply chains of the OEMs that we work with to access their tools, their scaling, because that's how we vet out the product for mass production, right? We can bring it to a certain point in our laboratories, but we can't simulate mass production until we actually get out there and do it.
So the startups provide essentially a bridge and a continuing bridge, basically, from flying bridge from MIT or the technology side of it to the companies. Excellent.
That's right.
I'd love to be able to just throw another dozen questions at you, but we got a few people here that I suspect have some questions as well. So why don't we open it up to the audience for a moment and see what they have to say. Carl?
I'd like to hear. Yes, thanks, Buzz. I have a question for both Air Liquide and Schlumberger. I'd like you to describe a little bit more what your strategies are around open innovation and accessing universities more broadly. Not just, both of you have strong relations with MIT, and we love that. But as you think about accessing the global innovation ecosystem and startups that are not only in the Cambridge area, but more globally, what is the strategy and the resources you're putting behind those efforts in your companies?
Sure, go ahead.
Okay. In Air Liquide, we started a venture capital to integrate the startups. So we already had acquired a few startups. Recently, last week, one from the Uban, we had some polymeric startup that was integrated into company with the 25 people, which is very traditionally, it is not the approach. We are a French company, very conservative, moving away from that one. Understanding the open ecosystem is a key part we need to integrate. And we went into this venture capital, and that is looking into the startups, whether linearly, vertically integrated into our portfolio, or it can be added into additional or adjacent businesses where we can expand our territories. So all those things are open, which is something different from when I joined in Liquide in 2007 to now. Totally it has changed the playing field. That gives us a much more opportunity internally for us in going into the adjacent areas. Today, my focus is on semiconductor, but at the same time, there is a lot of push is there. What are the other areas we can take this portfolio of molecules what we made and apply it to the other areas? And going back on one of the things Kripa has mentioned, we not only say the potential solution, we have also doing the prototyping. In Air Liquide is not a chemical company, it is an industrial gas company. The molecules have been identified by the researchers who came out and told that, hey, we want to start this kind of a business. We are not part of the those business line. So researchers have given me some seed money kind of thing, and they made the molecules and they went to the customers and promoted them. But they said that, okay, you're given 10 molecules, out of which one is the best? Then they took back internally and we started evaluating the process flow. We don't make chips, but we do all the things in order to identify that one molecule. Now we won't go and show the 10 molecules. We say, we screened it, but this is the best solution. And not only the molecule properties, here is the film properties. So they can take that one molecule and go into the integration. I think that is a key. Most of the time, even I worked in my past, when I was a researcher, integrating with one startup for one chemical molecule. They had a lot of hopes. They said, this is the thing, it will solve all the solutions. They wanted to get it to the market very quickly. There is no piloting, no scale-ups, and we spent almost 2.5 years on that one. Okay, after that, we had to pull back because the considerable amount of the resources and the expectations are mismatched. So I think one has to understand upfront, when we identify a solution, if we can have a prototyping, that will give much more leverage going to talking to the big companies. Anytime we bring a molecule or any solution, we think a lot on the long-term strategy. We have shareholders whom we need to address and how we do our investments also.
Very good, thank you.
Yeah, what I would add to that, so from Schlumberger's perspective, we're a very diverse company. We have more than 140 nationalities in our R&D organization, and we believe that's a strength, a tremendous strength, because these people have come from very different backgrounds, different education environment, and they bring these different perspectives. So our R&D organization reflects that. We're quite discreet, and we're spread out in many different countries in the world, and we try to find and locate our centers near very, very strong technology and scientific places like here, like in Boston, but also like in Moscow and Novosibirsk and Beijing and so on and so forth. And so it's very important for us to make sure that we are linking with different places, both for technological approaches and just different philosophy of problem solving. At the scientific level or the engineer level, the individual, we like it when people create strong personal relationships with individuals in those organizations, whether it's university or some of the startups. And we believe in literally investing, giving the individuals the time and the effort to build strong relationships to, again, create these enabling technologies and solve problems. And I think we have examples of many, many year relationships, spanning in some cases people's entire careers, and we really value that. And this often takes the form of support for students. It may be projects. We take the kind of like a reverse postdoc, industrial postdoc placements. And I know that over time, many of our employees have ended up migrating into faculty positions because some of those relationships were very strong. So. Yeah, we sure do. In fact, I think a number of the people in the room are familiar with the folks that run that. And yeah, that's been a really interesting part because we started that probably 6 or 8 years ago. I don't precisely remember. But it's been very eye-opening to the world of VC that they've gotten exposed to and the networks and the connections that has all created. So we also try to adapt. We have traditional internal R&E groups like the one here in Cambridge. We have engineering centers that do product development. We have industrial liaison groups. We have, like the VC things, we have little university liaisons, a lot of things, and we continue to look for what are more effective ways of doing that. So we're very open to ideas. Yeah.
Mm-hmm. Yeah, you've been in Cambridge for quite a while now, have you not?
7 years.
7 years, yeah.
If I may add, the fact that you have an MIT Startup Exchange, The fact that you have an MIT Startup Exchange is a good entry point to check who is starting a startup, because that's what we monitor. So as a fact, I've encouraged some students who came to see us, how do we get to talk to MIT, to Schlumberger? And I say, join the MIT Startup Exchange because we will find you.
On that note, may I bring in a question? I never
Absolutely.
do this, but I'm so curious about your perspective from the startup side of this. I work with many startups, and it's so interesting that our startups, in most cases, take a lot longer to reach sort of fruition or maximum, whatever, potential and momentum, certainly, than many other startups in other fields. Could you speak a little bit to how you think about that, and how you feel about that, and what we can do about the perception that a startup needs to succeed in 18 months?
18 months is a pretty aggressive timeline.
Well, I was just in Silicon Valley. This is how they feel.
Sure. If you're developing really revolutionary ideas, new materials, I think just developing the material itself takes quite a bit of time. But once you've developed that material, introducing it to industry and finding problems that it can solve really starts to accelerate that process. For us, I think really the key to success is very close collaboration and a lot of feedback. So I have weekly conversations with our partner OEMs where we're talking about the progress we're making and how it addresses their problems or doesn't. And so that's our ability to really fast track and bring things through is tapping not into our own creative bias in generating solutions, but tapping into their knowledge and their history in their specific industries. They've solved many problems that we might face as we go to scale up, for example. And so trying to solve that on our own is not particularly efficient, right? So it's about not being afraid to open up and say, hey, we're actually having a problem, and here's what it sounds like, and is this familiar to you? Do you have people that you would recommend that we talk to try to resolve this quickly? And that's been very effective at overcoming problems along the way.
Interesting.
I wanted John's.
Yes, I was going to add that it is an interesting challenge, right? Especially when you're venture-backed, right? Because there's always the pressure to move quickly, get product to market. And sometimes I think that's counterproductive, and maybe you end up taking longer because you have a pressure to commercialize something before it's ready, right? And so I think you've got to have the right balance of just recognizing that for a new material technology, it does take time to get the basic performance and capability of those materials to a stage at which you can even really consider commercializing it. And I think, looking back, obviously it's easy in hindsight to say, geez, if we'd done a few things differently, we might have gotten to where we are now faster with less money. And but I think there are some lessons to be learned there, and it's just a fine balance with the VCs looking for getting a return quickly from the harsh reality of this is going to take time and requires some patience, and maybe we should move a little slower to allow things to really incubate and gel to a point that you know exactly what the right way to go is, rather than rushing down a certain path too soon.
Mm-hmm. Yeah, I certainly recognize and appreciate the challenge associated with capital and capitalization for hardware companies. Software, IT, software as a service, the venture capitalist can walk in. It's a very, very cash efficient process. It's very, very small footprint, and you're in and out in 18 to 24 months. It's not the reality with materials and nanotechnology. I think Vladimir talked to that specifically. We had a question over here.
I would just highlight as a maybe way to point to the question, which is that despite the long time that MIT companies do take, because we choose to adopt problems that are harder than typical problems, the typical success of an MIT startup significantly surpasses the industry average.
Right.
So if it comes to successful exits, MIT startups are much more likely to do so than just any other startup you take.
Mm-hmm.
And I think I also want to add that if you're able to plan things really well in terms of thinking about think about your products as Gen 1, Gen 2, Gen 3. Like, we didn't want to solve the oil and gas problem where, on day one. If we were to think about pipelines, which, should have a life of 30 years, we wouldn't have gone to market that quickly. So we need to really think about segmenting the market and really go after those applications that also have a lot of value, right? So that you can you as a startup can make money and keep, then go to the next industry and next industry. I think that helped us a lot to get to product. Like we were cash flow positive in 1 year, and then we were able to get to now we'll have products on the shelf end of this year, and so on. So I think planning both technologically but also markets and the business models, because sometimes the deals have to think out of the box in terms of the way you make the deal.
Right.
And so having some confidence intervals on the business side as well, not just on the technological side, saying, hey, if I do this, what kind of money am I going to make? I need to know that up front so that I can go and work on that product. Right? So all those things play a very important role in really accelerating the technology and having impact.
So it's not just the science and technology, it's the marketing and the management as well, which is why we spend so much time at the Sloan School, I guess. Question?
It's very nice to hear that all these new technologies are coming. I'm from a larger corporation, VC arm of a corporation. So one of the areas we are looking also nano. That's a good thing that all these technologies come in. But one of the concerns that we have within the company is the environmental and health and safety of these nanomaterials. So at what point the university researchers or the startups or other things looking for these EHS issues, PPE, safety of the operators, safety of the consumers, is it a responsibility of the end customers, the corporations like us, when we take to the market, or you have that data ready when we talk about the technology to provide these EHS nano safety issues? So just to the panel.
I guess I love to highlight that we've been using nanotechnology for centuries without asking those kinds of questions. And it's the right question to ask. I think we should ask, is the whiter than white detergent really safe for us, right? Because the phosphors are nanoscale inside it. Are the smells we are smelling that are every single smell you ever sensed is 1 nanometer in size, are those smells really affecting us because they can go through our skin and can get through our blood system and then from there to the brain? Are the clear suntan lotions that have nanoparticles of titanium dioxide, they can go and breach the skin, get to the blood, get to the brain, bleach our brain. Any pigment you ever touched, right, is nanoscale. These are questions for every single item we use. It's not just for these new technologies. And indeed, just like we have been addressing the safety of the products we launched in the past, these technologies are no different. We should similarly make sure that they are safe and rationally produced. I mean, there is also, I highlight, for example, we use lead these days to make really efficient solar cells. And people can say, well, you're using lead. I'm like, well, yeah, we're using lead. But you know what? In a millimeter of soil, of non-polluted soil, you can find enough lead to make my solar cell. Now, is that good or bad, right? If I drink coffee every day, in a matter of a year, I drink enough cadmium to make a display. Is cadmium good or bad, right? I mean, right, there is, I think it's rational to go ahead and ask questions. I think it's also important to put it in perspective on how we use the world right now and what do these technologies imply for the either reduction of cadmium or reduction of lead or looking at the full cycle. I mean, I think, John, I don't know if you want to comment on the light bulbs or on the...
Well, yeah, in a lot of areas here. I mean, what I'd say is, certainly, in working with, we have two challenges, being nanotechnology and also utilizing cadmium, which is a heavily regulated material. We've had to be proactive from the beginning in these matters, right? And so I think from the start of the company, we took, EH&S very seriously within the company in terms of, first of all, from our employees to ensure that they're operating safely. We collaborated with OSHA on doing studies to ensure that, we are containing the materials in the lab where they're supposed to be and not coming out and migrating into the offices and so forth, and having the appropriate procedures in place so that as we bring these to our customers, we can train them and show them the safe way to use the materials. And then on the other side of the whole cadmium story, we've had to be extremely proactive and diligent of working with various third parties to do studies and analyses to demonstrate the value of, we're actually taking what can be a toxic material, consuming it and packaging it in a safe way, and then by delivering products that are more energy efficient, reducing the amount of electricity that has to be generated, which actually in burning coal releases far more cadmium to the environment than the tiny, minuscule amounts that we use in our products. And so doing that type of whole life cycle analysis, and we've been extremely active in it because you have to, right? Because we go to our customers and there's this perception of nanotechnology is dangerous and cadmium is a terrible material, we can't touch it. And
Any questions from this side of the audience?
So it's very exciting to hear about this new center that's coming. And I have a question about, when we started the talk, I forget at the very beginning, that there's over 1,000 startup companies and 7 clusters, and nanotech is the smallest, only 34 companies. And we're going to have this big new center. And I'm wondering about, what are really the new ideas, right? So the new ideas in nanotech. And looking backwards, are the things that have been coming out really what you expected 20 years ago when we first started talking about nanotechnology? But looking forward, what are the new ideas? And maybe you talked about tools being an enabler. What are the new tools and what might they enable?
I feel like the question is pointed to me, so I'll start. But I would say, as a start, I never expected Liquide would do what it does. I never expected there would be a company called Liquide that is capable of doing what it does. And I would never really expected that this is the large area nanotechnology utilization, if you asked me 5 years ago, before I ever met Kripa, right? So what's remarkable about Kripa and all of our young faculty is they come out of a blue with ideas that we really haven't foreseen. This is not a way that we think about. Soon I expect, well, give us 20 years, but there will be anti-gravity, right? I mean, there is, the way things are progressing. The quantum computing, for as futuristic as it sounds, we have 2 people at least, maybe 3, that are rationally thinking through the process on how to do that. What does that mean for the computational systems of the world? Complete change, right? Going from deterministic to probabilistic way of computing and reducing the energy significantly. When it comes to coatings and surfaces, man, what we imagined before when it comes to anti-fouling, being able to make sure that they are hygienic surfaces, making sure that you can, any surface you touch should be active in some way. Is it active electrically, optically, mechanically? Those things we can now do in the lab, and likely in 10 years they can become a reality where is it solar cells that are everywhere, or LEDs that are everywhere, or mechanical surfaces that will, with micron motion, give you tactile feedbacks. There are many, many things. And the fact that I mentioned that 51% School of Science, 67% School of Engineering, there are thousands of examples, 2,000 examples that could be cited. Yeah. And likely 10% will get of them will get somewhere, meaning about a couple of hundred companies.
Yeah. Let me give you
what we're doing today, and they will do another 2,000 next year.
Yeah. Can I add to that just for a second? Basically, back in '82, when MIT was arguing about whether, in fact, to embrace this thing called the Whitehead Institute, we didn't know what it was. We didn't know what it was going to do. Look around and look at what it did. I don't think you can actually predict exactly what's going to happen, but it's the kinds of things that you exactly pointed to. Liquide, where the heck did that come from? But when you look at essentially nanotech and you think about it in energy, quantum science, electronics, health, life science, in manufacturing, when you count only 34, I think you're missing essentially by a factor of 3 or 4 the number of companies that are actually involved in technologies that are founded on nanoscale technologies. Question?
One of the questions for discussion in this poster in this handout is what are the opportunities for collaboration among industry, universities, governments, and startups? And we haven't really talked about what role government could play, so I was wondering if anyone in the panel would like to answer that question.
There are many roles government can play, right, as a convener. It's really nice to have matching funds, for example. So an example would be there is the manufacturing centers that are being launched by the Obama administration. There's the latest one, and I'm fairly familiar with it because my colleague Yoel Fink is trying to launch it. It's a center on fibers that we're trying to get here. Just to give you scale, so government will put in about $75 million into the center, but Yole has assembled 90 companies, universities, industry, states contributions that add up to about $475 million of additional funding, right? So together it's about $500 million endeavor initiated by the $75 million seed. Now, how much will MIT get of that? Relatively small amount, very, very small amount. But what we'll get is a tremendous number of partners, and we will coalesce a way of thinking about fibers and textiles that has never been done before, right? And we'll be able to place our people on the helm of redefining an industry that seems stagnant and kind of blue collar rather than really white collar, technologically advanced and omnipresent as it will be in a very different format from simply shirts and jackets, right? So that's what government could do. I think the other thing to ask is what national labs can do as already instantiations. And maybe a way to put that forward would be to ask, places like Lincoln Labs, that MIT Lincoln Labs, they actually make products, not in very large quantities. They're typically, few satellites, but few remarkable satellites. Like if you look at the kinds of technologies or, computers for Aegis destroyers, those are really hard to build the way they build them. And there are not too many of those, but you cannot get a better computer system in the world than what those guys have built from scratch in the matter of a few years by adapting their knowledge and technologies from elsewhere. So they could become the collector of the best practice, those national labs of ours. And as a result, could be the disseminators of what are the first steps in what could be innovation process of the best practice, allowing us not to spend time reinvestigating things they already know about. So that could be another mission, call it, for national labs.
Good question, thank you. Yeah, I think you hit it right on the head. We're running out of time, so I'd like to pose one last question to all of our panelists to respond to as we wrap up. And we've discussed all the possibilities, but what the heck is our neighborhood going to look like in 10 years, 15, 20 years? What are the opportunities? What are the challenges? What closing comment would you like to make?
For us as an industry, the advanced materials, the transistors as we know, another 2 generations are there, 5 to 7 nanometers. Beyond that, we don't know exactly whether carbon nanotubes are going to come or any other novel materials are going to come in the fabrication of the transistors. What will happen, still that's an unanswered question. It is open-ended. Everybody is looking into the 5 to 7 and 5 nanometer node. Beyond that, what has changed in the 2D transistor to 3D, there should be another explosion where the technology has to show a different path. So that is what we don't know. That will impact a lot on our ability to bring the molecules. Maybe they're going to be changing certain aspects. So we have to wait and see on that.
John? We'll jump around here, randomize the process.
Well, I think in our area in displays, there's going to be just the ubiquitousness of very thin, flexible displays.
Flexible.
And and we expect incorporating quantum dots for just beautiful display quality.
Of course, quantum dots.
Of course.
Definitely. Matt.
Yeah, so I guess I'll reflect on from the perspective of a cyclical industry where sometimes we have to figure out how to preserve skills and competencies, and sometimes we have to figure out how to grow really fast. And a key to growing fast is to have products and services that are extremely reliable and that you can teach people how to use easily. And so some of the things that we can do to increase reliability through advanced materials and more durable surfaces and better capabilities, these are the types of things that we're going to be interested in and looking for in the future.
John?
Well, I hope as we see more successes in nanomaterials getting into the marketplace, that will become easier to introduce them, that people will overcome some of the fears that they have around nanomaterials. They'll be more receptive to trying new things and fostering through them as they see the success of nanomaterials and sort of the beachheads where they're introduced.
So momentum. Yeah. Kripa?
I'm excited about the future. I think there are lots of challenges: energy, water, food, healthcare. I think the opportunities are endless. So I feel this urgency to both do the science but also take it to market. So I think I feel that the future is only bright, and
So the opportunity is now and impact is wide open.
Also now.
Also now. Vladimir, you get the last word.
Yeah, so I guess I'm thinking in about 5 to 10 years, from here all the way to 495, which is the second belt. There's 128 is the first belt of roads around Boston, 495 is the second belt. All of it will be known as Kendall Square. Because I think what we are seeing is a tremendous amount of drive for people to be here, to be immersed in this ecosystem, and it's that connectedness between individuals that, I mean, we are in the densest startup area in the world right here, this 1 square mile. That square mile will get bigger. And I think through that, one thing that we as MIT see is that there is a rhyme and reason for why MIT is successful. And this particular rhyme and reason can be quantified. What we started to launch is what we call a lab for innovation science, thinking about the actual physical processes that, like ecosystems that are enabling innovation to thrive. That will be figured out in about 5 to 10 years, at least the first steps of it, which will allow us to export it. And I think the blueprint of what Kendall Square rules are for innovating will be known as the Kendall Square rules that should be adapted elsewhere. And indeed, hopefully, we'll make the rest of the world be able to adapt our best practice and learn from them in the process.
So we're not done.
No, we just started.
Exactly.
We are at the Renaissance. We are at the Renaissance age of nanotechnology. We are at the Renaissance age of understanding what innovation is really about.
Yeah. So I get really the last word. I want to thank Trond and his team for basically creating the opportunity for us all to be here, for creating essentially the platform, and for catalyzing the discussion. Very, very helpful. I'm delighted to basically be at the interface between this and have an opportunity to participate. I want to thank the panelists for their contributions, and I want to thank you for your questions and your participation. Thank you.
So on that note, and as we're walking out, I just wanted to say that, you know, at each of these events, we can only feature as many as come forward, because there really isn't a limit to what we are willing to stretch this concept to include when it comes to audience participation. So I wanted to say that, you know, in addition to the 2 multinationals you have in front of you here, that we are already working with connecting to innovation on campus, and soon to be, I think, connecting directly to startups in some creative fashion, either through the platform or otherwise. So look out for that. We have representatives from Sabic, Samsung, Shell, IHI, Henkel, WL Gore, and 3M in the room. So I wanted that stated for the record. This is a very, very unique place. I'm not just saying that because I created this place, but if you objectively look at this, there are no other workshops on the planet where you can find 1/3 company founders, 1/3 brilliant minds who are also professors at MIT, and 1/3 executives from industry players that are shaping and moving the future. So on that note, and on the last note, that 1 square mile will soon be very much larger, coming from MIT's nanotech czar. I think that we have covered some paradoxes enough to last us for a day. And see you again either at our 19 November R&D panel on startup exchange and related questions between how to improve communication between industry and startups, or on the 1st of December for the MIT Ecosystem Conference at the Media Lab. Sign up early if you're a startup and participate. It's free. If you have absolutely no relationship, you pay a lot of money, but you get a lot of benefits. Thank you very much, and have a good day.